Welcome students. So today we are going to see about oscillators. The oscillator is a electronic circuit which generates an AC output signal without any AC input signal. It's called an oscillator. So it requires only the DC biasing signal and it does not require no input, AC input. By that way you are getting the AC outputs. So oscillator converts DC to AC signal. We know already rectifier is converting AC to DC. So here in oscillator, it converts DC signal to the AC signal and it works only in the positive feedback. This oscillator must be satisfying the Barkhausen criteria. So he gives the two criteria conditions. One is total phase shift around the loop is 0 degree or 360 degree or integral multiples of 2 pi. Then the loop gain will be A beta will be equal to 1. Once you substitute in that formula of positive feedback, that is AF will be equal to A divided by 1 plus it is a positive feedback, so 1 minus of A beta. If I'm substituting A beta equal to 1, the entire answer become infinity. So the feedback gain I'm getting is infinity. So the total oscillation will get sustained. Then if condition sustained oscillation value will be greater or lesser means what happened to the oscillation. If A beta will be less than 1 means it will be a decaying oscillation, and if A beta will be greater than 1 means it is called a growing oscillation. A beta equal to 1 means it is a sustained oscillation. It is a Barkhausen criteria. And oscillator classification, we have two types. One is harmonic oscillator and relaxation oscillator. Harmonic oscillator is also called as a sinusoidal, and here it is a non-sinusoidal oscillator. Sinusoidal oscillator means the output waveform must be a sine wave, and a non-sinusoidal waveform means you can get a triangular waveform or sawtooth waveform or a pulse waveform or a square waveform. Likewise, you can get. So, other than a sine waveform, you can get their answers. So, these are multivibrators or comes under this category: monostable, bistable, and astable. And here, harmonic oscillator, we have three concepts. One is RC phase shift, RC oscillators, LC oscillator, and crystal oscillator. So this crystal oscillator, it is made up of quartz material for high frequency of oscillations. And RC phase shift, it is having RC oscillators, that is, it consists of resistor and capacitor in the tank circuit. It is of two types, RC phase shift and Wien bridge. LC oscillator, nothing but it consists of inductor and a capacitor. Three types are coming under this category: Hartley, colpitt, and clapp oscillator. So let us discuss about the LC oscillator derivation. So normal BJT have to take with voltage divider bias. Then there is no input. See here, there is no input here. Output has to be connected to the input with the feedback tank circuit. So I am introducing the three letters, that is Z1, Z2, Z3. Three reactive components I may be introduced in your tank circuit. It may be an inductor or capacitor. Based on the type of oscillator, it will be differ. If it is a Hartley, both Z1 and Z2 is inductor, Z3 is capacitor. If it is a colpitt, Z1 and Z2 is capacitor, Z3 is a inductor. So I redraw the tank circuit alone. So thereby I am getting Z1 and Z3 will be in series and it is parallel with your Z2. So by finding, the first step is to find the beta. So to find the voltage divider rule, Vf will be equal to total voltage is V0 into corresponding resistor divided by sum of the resistor. So thereby beta, we already know the formula, beta will be equal to Vf by V0. So thereby Z1 by Z1 plus Z3. Then the second step, you have to find AB. So have to draw the voltage amplifier feedback diagram as usual. So thereby applying voltage divider rule in the V0. So I want V0. So V0 equal to total voltage AV into VI into corresponding resistor is ZL divided by ZL plus R0. So thereby V0 by VI, that is I am bringing this VI to here. So V0 by VI, we already know it is called AV. So here also we have one more AV. AV into ZL divided by ZL plus R0. What is ZL actually? ZL is a tank circuit, meaning that Z1 and Z3 is in series and it is parallel with Z2. So parallel, after getting the parallel answers, you are having the equation of ZL will be equal to Z1 plus Z3 into Z2 divided by sum of all the three impedances. So we have find the beta and we have find the A answers. Now the condition for sustained oscillation is modulus of A into beta will be equal to 1. So we have to multiply both the answers what we are getting in the previous equations. So after substituting all the ZL answers and then I cancel it off, then finally I am getting this equation. And then substitute Z1 equal to Jx1, Z2 equal to Jx2, Z3 equal to Jx3. Once I substitute, we know already J into J is -1. Once I substitute everything, I am getting this term. Now there is the next 2 minutes work is to find equating the real part to 1 and imaginary part to 0, because your right hand side is 1, so it is take it as a real part. So all the real term as must be equal to 1 and imaginary term, only this part is a imaginary term. I make this term equate to 0. So thereby my first condition, as for my equating the imaginary part to 0, I am getting this answer, and equating the real term, I am getting this condition. So this is the main important condition for sustained oscillation. Now we have to introduce the three types of oscillators. So Hartley, colpitt and clapp crystal oscillators. So normal up to this portion, it is common for all the diagram. So because it is that common voltage divider bias using BJT, only the tank circuit is going to be differ. Clear? And here see in Hartley oscillator, two inductors, one capacitor, and in colpitt two capacitor, one inductor. Clamp is 90% same as colpitt oscillator. There is two capacitor in the above and then inductor. Only the new third capacitor has to be introduced series. Then this is a crystal oscillator made up of a quartz material. The specialty of Hartley oscillator is it can be suitable up to 30 megahertz. Here it is called it is 30 to 300 megahertz. Here the frequency of oscillation is to be variable, and this one is possible. It is not possible in all other oscillators. Crystal we know already it is suitable for very high frequency, maybe in terms of a gigahertz. Then the derivation. So we just now we find out equating the real imaginary part, we are getting this equation. So write this equation as the first point in all the oscillators. Then you have to introduce who is x1, who is x2, who is x3. In Hartley oscillator, x1 and x2 is an inductor. So inductor can be represented by omega L1 plus omega L2. Inductor x3, actually it is an imaginary part. Jx3 is nothing but a capacitor. So can be written as capacitor can be written as 1 by j omega c. The capacitor can be represented as 1 by j omega c. So I am bringing j to the numerator, so it becomes minus j divided by omega c. So in all the term I am having, that is I am equating imaginary part now. So remove the j letter, thereby I am getting that minus 1 by omega c. Clear? Then I have to equate and getting the equation of omega. Omega will be equal to 1 by root of L equivalent into C. So this can be written by F in terms of F also, and then L equivalent will be equal to L1 plus L2. Similarly for colpitt here, X1 and X2 is a capacitor and X3 is a inductor. So like the same way we have to solve and we have to get the equation. For colpitt, the X3 is inductor series with the capacitor. This is one more term. So include just the same way you have to solve it and you get the equation. Crystal oscillator, you have to find two things. One is a series resonant frequency and parallel resonant frequency. So this is the equivalent diagram of the crystal oscillator. A single crystal consists of two branches. One is a series leg of a RLC component and a parallel with a capacitor. So this is a parallel capacitor, so it is called CP. And here RLC all are connected in series, so it will be RS, LS and CS. For series resonant frequency, have to make the reactive component of series leg is 0. In the series leg, we have three members, but only we have to make the reactive component to 0. So reactive component means it may be an inductor and a capacitor. So omega S into Ls minus omega S into Cs will be equal to 0. Then we are getting omega s equal to 1 by root of ls into cs. Immediately I have to write in terms of fs. Then the job is to find quality factor of series resonant crystal. So omega L by R is a common formula. It is a series component. So it will be omega S Ls into Rs. The second step, we have to find the parallel resonant frequency. So omega P into Ls. Because we have omega parallel resonant frequency means you have to make both series leg as well as the parallel leg reactive component has to be 0. Series and parallel leg reactive component has to be make 0. Thereby I am getting in the parallel leg I am having the capacitor. So omega P Cp is 0, and the series leg I already have the inductor and capacitor. So make sure that you have to use the letter omega P. Previous case you are using series resonance, so omega S. Now it is a parallel resonance. From that you have to calculate omega P and immediately FP have to write. Then quality factor, you know already the formula omega L by R. So here Omega is a parallel frequency, so omega into P, remaining thing are series components. And then Hartley colpitt clapp, we have one more condition, that is by equating the real term, I am getting the equation of AB is greater than x2 by x1. So I have to just substitute x2 is my inductor. Hartley means both x1 and x2 is inductor. And colpitt, it is a capacitor, so it is a denominator term, so it will be get reversed. So C1 by C2 you are getting. In clapp oscillator, both x1 and x2 as usual same as colpitt oscillator, so C1 and C2. So thank you, students. So this is the concept of Hartley, colpitt, and clapp oscillator and crystal oscillators. Thank you, students. All this category comes under the LC oscillators.